Hello, and welcome back to Statistics for Psychologists. Today, we will revisit your knowledge on descriptives. We will use descriptive data to do some analysis, make some inferences about the distribution of, for example, male and female teachers. And we will use chi-square tests to test these ideals statistically. So, two kinds of chi-square test will be visited today. First, the easy one, the one variable case. Later, we will turn to the two variable chi-square test. They're both non-parametrical tests for frequency data. So we will only deal with categories and how many observational units are there in these categories. Let's start with talking about frequency data, the contingency table. So the data to be analyzed are simply frequencies, and variables are the qualitative variables, nominal scales or ordinal scales, or if we have quantitative measures, we do have to categorize them. For example, if we have data on how many cigarettes and somebody smokes per day, we can make a heavy, light, and non-smoker category out of this data. We will make inferences about the population frequency distribution, basically how many people do we think are smokers, non-smokers, and how does the observed frequencies relate to these assumptions. So the chi-square test is basically a hypothesis testing, just like the t-test. But here, the difference is that the H-no states that the population proportions falling into the various categories are equal to certain predetermined values. And we have one single alternative hypothesis, which includes all other possibilities when it's not the case, right? So our H-no can be, for example, if we have 4 categories, we think that there's some percentage in 1, 2, 3, and the whatever categories, okay? The GS says that we can have 12 categories if we have a large enough data set. Don't make too many categories because you won't have enough data to fall into these categories. The easiest case is when we have 2 categories, yes or no, male or female, smoker, non-smoker, okay? This is a good example of this case. We think that there are more female teachers and lower education, and we will probably be right. So, thus, our null hypothesis is that there are equal number of males and females. This is what we want to reject on the long run. Remember this hypothesis testing sequence. So, we would like an alternative to become true, but that's why our null hypothesis is set up this way. The hypothesis testing for the chi-square test is similar to any other testing. We put in the sample, we apply this chi-square function where we have the observed and the expected values. I will get to that in a moment, and also the contingency table. We do the analysis, we have a single critical value for the chi-square test at a preset level of significance. This is very similar, only here we don't have a two-sided test, we just have one single critical value. No two-sided distribution here. So if the chi-square result of our actual calculation is smaller than the critical value, then we keep the null hypothesis. If the calculated value is higher than the critical chi-square value, then we reject the null hypothesis and keep our preferred alternative hypothesis. The critical values for the chi-square test are set up in this table, but the SPSS programs will give these to you and will give you an exact p-value to work with. So let's see this contingency table because it's quite important for the one variable case, the one sample chi-square test, it's also called. And this is still a good example. H null is that there are equal number of males and females, but of course we know we test much more female educators if we take a random sample. In the so-called contingency table, and this is a very important thing to know and to be able to draw, so I used to tell you to draw the case variable matrix, also the scatter plot. This is another thing that you have to know to set up a contingency table with the data. In the contingency table, we have the categories in columns, and in the rows, in this one variable case, we have the observed frequency, and right underneath in the next row, we have the expected frequency. So this is what we measured, the N1 and the N2 for males and females, and there's much more female teachers. But this is what we expected, the nus, nu1 and nu2, based on the null hypothesis, 25-25. Now the chi-square test will simply seek out the difference between these numbers, and this will be done in SPSS using this very, very simple function, the N1s and the nu1s, and then summing it up. So N1 minus nu1 squared divided by nu1 plus N2 minus nu2 squared divided by nu2. And if you have more categories, here we have only 2, you have to continue this summing. The result is a single value, right? This is the chi-square result, which you can compare to the critical value, but SPSS will do this for you. So here the chi-square result is 32. That's such a high number that we know that this will be significant. Because similarly to other tests based on the degree of freedom, we have to compare the critical, we have to set up a critical chi-square value and compare our calculated chi-square value to it. But here it's an important difference, and you do have to know this. The degree of freedom is not based on the number of elements, but based on the number of categories you're testing. Okay, so here the degree of freedom is 1 because we have the number of different categories minus 1. So 2 minus 1 is 1. So here for this degree of freedom, the critical chi-square value is 3.84, and it's definitely lower than our calculated 32. So we will have a significant result. Again, if we put it in the hypothesis testing and we have this 3.84 as a critical value, our tested value is definitely higher, so we can reject the null hypothesis and conclude that there are more female teachers in education. Not a surprise. Now, this is very important. For the chi-square test, we have a very important criteria. First, we have to use the kind of variables we already talked about. Second, we do have to check, this is our results and numbers, but we do have to check if the expected values are lower. Sorry, we have to test if the expected values are indeed higher than 5. Okay, this 5 is a preset value, and definitely 25 and 25 is higher than 5. But we have to check this whenever we do a chi-square test. Why? It goes back to the number of elements. If you have enough data, if these numbers are very low, for example, if we were testing 5 people only and not 50, then these expected values would be so low that the chi-square test cannot be used, is not valid for the testing. So just remember that the new values in each cell has to be higher than 5. Just in brackets, in SPSS, when you're actually testing it and you have more than 2 categories, the golden rule is that in 75% of the cases, this test criteria has to be true. So it's okay if, for example, in 4 cells, in 4 different categories, you have one that has a value which is lower than 5, but the others have to be higher than 5. Okay, so let's conclude our results. The chi-square test here shows that the proportion of male and female teachers in lower education differs significantly. That's our chi-square test result. There are more females based on the 50 subjects in our survey. Chi-square test result and p-value that you also have to report. Okay, so let's see some real SPSS results for the chi-square test, and you will probably learn more of these on the practical. So here, for example, in male and female observed and hypothesized values, we saw this difference, what I just showed you. And the total number of elements, the test statistics, degree of freedom, and it is a significant result. Okay, also this is the notion for the criteria. There are no cells that don't are not okay for this criteria, so it's okay. Let's see some other examples. Are there equal number of male and female newborn babies based on a representative sample of, let's say, 550 boys and 480 girls? We can kind of see the difference, but is this difference significant? So we set up the contingency table. We have the expected values, which are equal. That's what we want to reject. And we have the observed values. We can either calculate or we can revert to SPSS to calculate the chi-square result for us. So the chi-square result will be 1.6. The degree of freedom is again 1. And thus, this critical value is 3.841. What could be our result? What do you think? Is it a significant difference or not? Or not, because the calculated value is below the critical value. Thus, we cannot reject our null hypothesis. We have to keep it. And based on this sample of 1,000 newborn babies, we can conclude no significant differences between the sex ratio of the newborn babies. Here, you don't have to report any descriptives or chi-square test result, just the fact that you didn't find any significant difference. Let's check another example. Is there a color preference in people's choices when buying certain products? For example, here we saw 25 people choosing red, 23 blue, etc., etc., etc. Can you draw the contingency table? Stop the video and try it. Okay, so we have the red, blue, green, and purple categories here. 4 different categories with the expected frequency of 100 divided by 4. Let's check the criteria right away. Is there any cells where we see a nu lower than 5? No, so we're fine. Here are the observed frequencies, and we can check the results if we calculate the chi-square test. I'm not going to do that now. try to do it on your own. Now I pose you another question. Is purple twice as popular as red or blue? This is a tricky question. In fact, you can solve it many ways. Here is one. So here I drew the contingency table as red, blue, and purple, okay, because these are the categories. But now watch. Here on the expected values, I put twice as many in the purple slot as to blue or red. Okay, you could also make two categories, blue or red or purple. Okay, but this is then in the or instead of the or I should have had and. But here I have or, so either red or blue as compared to purple. And here are the actual observed values. You can take a guess whether 42 is significantly different from not these categories, but the expected value that we have here. Okay, please do this. We will get back to this when we, the solutions when we get on the consultation. Let's now turn to our other chi-square test, the two-variable case, where we also test non-parametrical data, frequency data. But here the contingency table will be a little bit different, and we will draw a table for something we call a bivariate frequency distribution. We have two aspects to consider in these kinds of hypothesis testing. We will talk about the null hypothesis of independence and this 2x2 chi-square test. We also call it bivariate chi-square test. Okay, so again, the data to be analyzed are frequencies. We already talked about there. But here we have two different, not just one, for example, male or female, but we have another aspect to talk about. But the scales should also be qualitative scales, just like before. And the same inferences we're making about the population frequencies that fall into the different categories. So again, a good example, because that's the easiest way to understand this. Now we're talking about the sex ratio of teachers and doctors together. So the question is there a difference in the sex ratio of teachers as compared to that of doctors? Okay, so the teachers we already know. We know that there are more females, but how about the doctors? Are there more males or females as compared, or okay, we can see that there are more females in doctors too, but is this ratio significantly different from that of the teachers? Okay, so that's the logic in the 2x2 contingency table. And here we have really a 2x2 split here. Okay, we have males and females, teachers and doctors, and we simply put in only the observed values. Why? Because in the contingency table, we will have a separate table for the expected values. The rest of the testing is very similar to that of the chi-square test we already talked about. The H-null again states that the frequencies in the population is same for all the rows, okay? And basically saying that the distribution is similar for males and females in the doctors as compared to teachers. And as usual, the alternative includes all other possibilities. Question is here, if the teachers are 10% as compared to 90%, is that significantly different from the 30-70% we observed with the doctors, given a certain sample size? Because a sample size, as always, is important here too. So here, step 1 is to calculate the expected values. Similarly to the previous example, we simply distribute these evenly, because that's what the null hypothesis dictates us. And if we have 100%, 100 as a number of elements for total, and here we have 40, we simply multiply these and divide it by the total number of elements, the 200. So 100 times 40 divided by 200 will be 20. And we call this N11 and Nu11 for male teachers. Okay, we do the same with all the rest of the cells. And thus we have 4 cells for the number of elements here, N's, and 4 cells for the expected values based on the null hypothesis. And we do exactly the same type of chi-square calculation with acknowledging the test criteria, which here is perfectly okay. We can continue with the analysis. You don't have to calculate chi-square test by hand. The SPSS program will do it for you. Just make sure you choose either the 1 variable chi-square test or the 2 variables, 2 by 2 chi-square test version. So the chi-square value is calculated. That's the formula for it. It's really not that difficult, because the logic is exactly the same as in the 1 variable chi-square test. We're using the N's and the Nu's in order to calculate for the 4 cells, which we can sum up at the end. I'm not going to do that for you now, but the result is here a quite high value, 12.5. This is our calculated chi-square value. Let's see how does this relate to the critical chi-square value we have here. And this, you have to know that here we have a degree of freedom, but it's a little bit more complicated than in the 1 variable chi-square test, because here we have 2 rows and columns to think about, and the logic is similar. We have the number of columns minus 1 times the number of rows minus 1. Here it's an easy case, because 1 times 1 is 1. So still we will use this very well-known degree of freedom, which 1, which relates to this, you will know this critical chi-square value by heart, probably this 3.84. That's what we have to compare our calculated chi-square value to. Is it higher? Yes. So we have now, in the step 5, hypothesis testing, a significant value, because our calculated chi-square value is definitely higher than the critical chi-square value. So based on the data of 100 teachers and 100 doctors, using the 2 by 2 chi-square test, we can conclude that there's a significant difference of the sex ratio of teachers and doctors. Chi-square value, p-value. These are the musts in your conclusion. And now comes the important part where you explain, okay, I found a significant difference, but what is significant? Well, there are more females, 90%, among teachers as compared to that of doctors, because there's only 70% of females among the doctors. You can also put this to a neat chart or provide a table with the percentages. Always use percentages and not raw frequency values. It's much nicer that way. It's easier to compare. Okay, just a note, the number of observed frequencies may vary, okay? And chi-square tests the ratio of the rows or columns. by that chance. You don't have to compare 100 teachers to 100 doctors. You can do this. For example, in this problem, we have 80, the total of 80 boys and girls in math, but 240 in psychology. That's absolutely no problem. The chi-square test will be performed correctly once you acknowledge your test criteria. Are there enough expected values? Yes, definitely. Here we have enough, more than 5 in each case. So chi-square value is quite large. Degree of freedom is again 1. This is your comparison value. What is your conclusion? Hopefully you said that expected, based on the comparison of expected and raw frequencies, using data from 80 math and 240 psychology applicants, the 2x2 chi-square test shows that there's significantly more females applying for psychology, not surprisingly, than to math. Okay, the chi-square test was significant. One note here, when you're presenting percentages, just watch that the sum of all rows and columns add up to 100, because rounding can be tricky sometimes. Okay, so these are the correct percentages that you should use in this case. To sum up, we've used and learned 2 kinds of chi-square tests. Make sure not to mix them up. Okay, the one variable case where you have just one focus, one aspect, and the 2 variable case where you have 2 subpopulations in which you're interested in some categories to compare. So these are the 2 tests, and thank you for watching.